Last segment we discussed about the trusses. In fact, we defined them, or in a way we characterized them. And what means is, when we say truss, what exactly should we think about? Okay, those members, those joints, those two force members, 2 points of connection to the systems, all those things. So those are important. And now in this segment, what we will talk about is how to investigate them. In fact, if you remember the last segment, we also talked about what exactly do we mean by the phrase investigating or investigating or analyzing a truss. Okay. So now there are two methods. One is called the method of joints and the other one is called the method of sections. We will discuss both of them in this segment, and it's a better idea to explain these methods through examples. Okay, so what we will do is we will take an example of a truss, a very simple one. Say say suppose we have something like, what happened? Say we have something like that. Okay, and now we know when we draw like these lines, what exactly do they represent. The 3D version, their 2D representation, and this one dimensional representation. All those representations also we talked about last segment. And now if I draw the joints, so these are pin joints which are very free and frictionless. Okay, and then we will include the, say, the supports. One is a hinge support or a pin joint, and the other one is, say, a roller support like this. And let's put some forces also. Maybe say this is, say, F1, and maybe say this one is F2. So these are two forces which are acting on a truss. This is a very simple truss. Okay, and then for the explanation purpose, we have taken this so that things will be clear. Okay, now what? Let's discuss whatever we talked about a truss in the previous segment with respect to this. Now all these things, let me give some names to them as well. See, this point is A, see this is B, C, D, and say E. Now AB, BC, AC, etc. We call them members, and these points A, B, which are purple colored, they are the joints, they are the pin joints. And we have also assumed that these members are massless. That means we don't consider their own masses, and that is why, because each of them have only got 2 points of connection. Every member is connected to the structure with only 2 points, and that is why all of them will be 2 force members, because we have also neglected the mass. Otherwise they would have become a 3 force members. Okay, so then what? And it's a rigid structure, because all of them are triangles, and then these triangles are connected through these joints, so it becomes a rigid structure. It doesn't move on its own, or with respect to each other. These links do not move. And then, yeah, one more point we had discussed, the forces are acting on the joints, not on the members. Yeah. Now, having discussed that, now let's say we have to analyze them. What do I mean by analyze? We were saying that, okay, how many members are there? Let me number them. Say this is 1, say this is 2, this is 3, this is 4, 5, 6 and 7. Okay, so there are 7 members in this truss, and how many joints? 1, 2, 3, 4, 5 joints. Okay, now each member, we said that it will, suppose I draw the free body diagram of say the link AB. Okay, so AB looks something like that, AB, and we can expect that the forces will be only like this. They will be along the line that connects the points A and B. In fact, the shape of this bar could be anything as we discussed in the previous segment, but we will represent them as a line connecting the point where the member is connected to the whole structure, and the line of action of the force has to pass through those 2 points because it is a 2-force member. So, that being the free body diagram of say link or member AB, similar things can be drawn for any of those members. That means what? Here I should have written B, no? Yeah. Now, what they mean is every member has got a force magnitude which is unknown, because the direction is known once we know the truss. The truss geometry tells us in which direction this force is acting. The only thing which is unknown is its magnitude. So, then it boils down to finding out all these magnitudes of the forces which are existing in all of these members. So, because now there are 7 members, so we have to find those 7 unknown force magnitudes. So, that is basically the idea of investigating or analyzing a truss. But then, yeah, let us go to the first method. Let me write it here. So, we are talking about the method of joints, or in short we call it MOJ, okay, the method of joints. One point, both these methods, the method of joint and the next one which we will discuss, the method of sections, both these techniques will use a step which is common. Okay, so that I will call say step 0, and so let me call a common step for both MOJ and MOS, and that is find out the ground reactions. Okay. Now, that is the first step, whatever method you choose to apply, but you have to do this first. Now, what exactly we have to do in that? See, here intentionally I have chosen the ground supports in such a way that maximum of 3 unknowns will come, and let us see what I mean by that. Whenever we try to find out the ground reaction, we have discussed that we have to consider the truss as a whole rigid body. Okay. Now, if I draw a reduced version of this, say here I will draw the whole of the truss. I am just representing it like this as a solid rigid body, and then the forces, I will call this say AX and AY here at this junction or joint, and say here I will say BY. Because that is a roller support, only one force will come, the force will not come, and that is what I meant by that. I have chosen 2 supports in such a way that maximum 3 unknowns will come, because we know that in 2D maximum we can write 3 equilibrium equations from which we can solve maximum 3 unknowns. So, if I use another say pin or hinge joint there will be 4 unknowns, and we will not be able to solve for them. Okay. So, that it will become a system of statically indeterminate structure. Okay. So, that is why I have chosen that. There are other considerations like symmetries which can be used to solve for them, but let us keep it simple to start with. We will not get into those complex things now. a statically indeterminate thing. So we will have a support system, the ground support system, which will provide maximum 3 unknowns like this. As and then we know how to write the equations, that is we can write a moment, 2 forces, 2 moment, 1 force, anything. So 3 equations we can write, which should be linearly independent obviously, and then we can find out these Ax, Ay and By. Okay. Having done that, so that's the common step, the first 0th step I will say, it is common for both. And then what you should do is you should represent this truss with not showing any of the supports whatsoever, just show the, say I'll do that here, just show the forces that are coming. Maybe there are external forces or internal, the reaction forces. Suppose the reaction forces are Ax, Ay, so Ay, then here it's By, and then external loads are like this, F1 and here F2. So this I'll call as a step 1. So this is say step 0. Now this is step 1 is draw without any support systems. That means we have removed these supports and only the forces are shown here. Okay. Now what? Now step 2 will be like, you know, here the method of, in fact up to this point it will be common for both method of joint and method of sections. Now what? Now the thing is, you have to consider the equilibrium of every joint one by one, because if the whole structure is in equilibrium, is in balance, that means every joint also is in balance under the action of the forces that are passing through it. Okay, so let's see here. So every joint, those 5 joints, they are definitely in balance. So let me number the joints here. Say 1, I'll put a triangle, 2, say 3, 4 and 5. Okay, so these 5 joints are with us, and then they should be in equilibrium. And we, in method of joints, what we do is basically we write the equations of equilibrium for these joints one after the other. But where to start is, so that's the trick basically. You should look for, the point is, in 2D for a given point, maximum you can write 2 equations, right, in Fx and Fy balance. Then you cannot start with a point where more than 4 forces or 4 unknowns are available. For example, if so these Ax and Ays are known, right? So this is known and this is also known, but then these 2 are unknowns which we are supposed to figure out. Then that can be taken up as a starting point. Okay, so but if let me show even the joints here. Okay, so like that. So now if I consider, okay, if I consider point, shall I go to the next page? Let me go. Okay, if I draw the point A, point A, so there, so one force is acting in the direction of, say, AB. Okay, I'll assume that it is a tensile force. You can assume anything you want, tensile or compressive, doesn't matter. At the end, the value, the magnitude, the numerical value which you will get, it will tell you whether your initial assumption was right or wrong. So let's assume that this was, say, FAB and it was a tensile force. Similarly, this is say FAC, which was also a tensile force, and then we had this as a force AX and this as a force AY. And let me draw even the joint here. So this is the joint A which we are talking about, okay? The joint A. So we are writing the equations of equilibrium of A. Now if you pick the joint A to start with, you are done, because see, there are maximum 2 unknowns, because and then I am now assuming that you have already figured out what AX and AY are. That means only 2 unknowns, and you can write 2 equations which are, you know, Fx is equal to 0, all the summation of x direction forces, and similarly Fy equal to 0. Now so suppose that means say x and y it's bad drawing, sorry. So if I consider my x to be this and y to be this, so sum all the forces in x, they should go to 0, and sum all the forces in y, they should go to 0. And for a given point in space in 2D, you can write maximum these 2 equations, not more than that. And that is why you should choose a joint where not more than 2 unknown forces are present. Okay, good. So in fact, the less the number of unknown forces, it is better. So if you can figure out a point where you can say that only one unknown force is there, so straight away you can figure out what is that force. And what happens if I pick a point, say this is point C. Suppose I pick point C to start with, what problem will I get? Let me see. Suppose I choose the point C here, right? Yeah, for its equilibrium. Now what happens is, say here one force will be there from BC, and from here one force will be there. So what was that? Sorry. So this is BC and then this is CD, right? So this is FBC, then this is FCD, and here we had chosen this to be a tensile, so this also will be tensile here. So this FAC, and here we will assume that it is FAE, and perhaps there is another force which is externally applied, which is F2. This is a known force, by the way. Okay, now if you choose to start at this joint, that means if you start by considering the equilibrium of this joint, the problem is there are multiple unknowns, 4 unknowns, and you can write maximum 2 equations for that point C. So you can never solve them at that instant. 2 unknowns will always remain like that, and that is why the method is to choose a point, to choose a joint where you will have maximum of 2 unknown forces, and then start from that, like this. And once you have figured this out, now you see FAB and FAC are known. Then which point should you go? Because here if I come after that, after evaluating this, if I come to point C, still I don't have this, so 3 unknowns are there. So it's a bad idea to come to point C, but let's see if I go to point B, what will happen. Let's say point B. So if I draw the free body diagram of point B, what are the forces which are acting? One is this FAB. So this is FAB, fine, and FBC, fine. So those are the only 2 forces, right? Anything else? FBD also is there, right? So that also we should put. FBD. Fine. So BC we are considering a tensile, so here also we are considering tensile. Fine. So then here, now this has already been solved for. This is a known force by now. Once you have finished this step of analyzing the equilibrium of joint A, you are done with that and you know this. And then how many unknowns are there? 2. And now you can solve for these 2 unknowns by using again 2 equations of equilibrium in x direction and y direction, and then it's done. So then you can solve for what is FBC and what is FBD. And now if you come to point C, okay, so from here we came here, right? After point A we came to point B, and then now if you go to point C, see what are the known things. This is already known from this step, FAC is known, FBC is known in this step, so this also is known. Now you are left with only 2 unknowns. So now again you write 2 equations in the x direction and y direction, you can figure these things out. Okay. So that basically is a very simple trick which is used to solve joint by joint by moving from one joint to the other, and then write the equations of equilibrium and solve them out completely. And then by the end you are done with all the member forces which have been evaluated. Okay. So that was about method of joint. But then there is a shortcoming in this method of joint. What is that? See, because we are using the equilibrium of a point, that's a joint, we are able to write maximum 2 equations, not more than that. But we can do better, right? Because see, in 2D, if we can write for a extended body which is not a point but some space which should acquire some, or which should have some space, then we can write in fact 3 equations. Then we can solve 3 unknowns at each step. So that's the idea behind method of section. And so in method of section, what is done is, instead of going from joint to joint, what we do is we cut imaginarily, we cut a section or cut the truss by an imaginary section, so that we will expose the forces maximum of 3 unknown forces. For example, here if I cut and then if I take these things away, so I will expose the force FBD, FBC and FAC. Okay. Now this FAB will be an internal force to that, and we do not have to bother about that. And then let me draw that in this page. So here what will happen is that section, if I choose, so it will be A and B, and then here I will have one, here I will have one, and here I will have one. Okay. So I have cut it like that. So this is an exposed force, this is an exposed force, and this is an exposed force. And then I know these forces which are acting here, AX and AY, and these things I will call, say, F, this is FBD, this is FBC, and this is FAC. So these are the 3 unknowns which we need to solve. And then you know that you can write 2 equations, summation of F forces in x direction should go to 0, summation of all the force in y direction should go to 0, and summation of all the moments about the z axis should go to 0. So that point you can choose to be any point. For example, if I choose that point to be point joint A, so you can write a moment about the point A for all the forces, so that from that you will get another equations. So then you are having now 3 equations. So in a given step you can solve for 3 unknowns. So it's a quicker method, and one is quicker and the other one is if you are not intending to solve for all the member forces. Suppose you are interested only in this member force, then why to go for solving everything? Because in method of joints you will have to solve joint by joint, and then you have to move from joint to joint to cover all the truss, full truss. But then if you are intending to find out only, if you are interested only in some of the members, then method of section is a much faster section method by which you can just choose a section judiciously, so that you will not expose more than 3 unknowns, and then you can solve for that. And then in fact a combination of method of joint and method of section is actually the best thing to do, and then you can use, once you know these 3 forces, you can go and solve for the single unknown which remains in a method of joints, like that. So that was about these 2 methods. And then something called there are some special tricks are also there, which are called the zero force members. So that we will discuss in the next segment, so that along with that, if you with that tool, or even it can be called as a trick or technique, with that even the solution process will be even faster. So that we will see in the next segment. But this was about the method of joint and method of section. They are nothing but writing equations of equilibrium, either for the joints in the question, or over a cut section of your beam, of your truss. See, in fact, one more thing I want to point out. Once you have cut a section like that, you could have chosen the left side or the right side also. So whatever is convenient, you have to look for that. Now once you have cut it, you have got a extended body. When I was saying an extended body, what I mean is like this. You can consider this part, this part which you have cut as a single extended body, which is in equilibrium under the action of these forces. One is this, forces are transmissible, one is this, and the other one is this. Under the action of these 3 forces, this and plus these 2 anyways, so the whole body, so this full body is in equilibrium. I should have drawn that in maybe purple, so that it will give a, yeah, so this full body, I think I feel comfortable in thinking like that. So this is the section which is in equilibrium under the action of these 5 forces, and you can solve for the 3 unknown forces involved in that. And as I was saying, you could have chosen the other part also, the right side which we have thrown away now. You could have chosen even that to do that. Okay, so that was about method of joint and method of section. We will see in the next segment to talk about what are zero force members and how they are useful in quickly solve some problems. See you in the next segment.